Have you ever stood on a platform as a train rolled in and looked closely at the wheels as they passed? They look simple at first, solid steel discs fixed to an axle. But look carefully at the surface where wheel meets rail, and something is slightly off. The wheel isn't flat. It tapers outward from the center toward the flange, angled in a way that looks almost like a manufacturing flaw. The wheel is conical. For a vehicle that runs on fixed tracks, that shape seems unnecessary. What does a taper do that a flat wheel can't? Trains carry hundreds of millions of passengers every year on networks, spanning hundreds of thousands of kilometers. Every wheel on every train shares the same basic conical profile. It is one of the most consequential geometric decisions in the history of transport, worked out largely by trial and error in the early 19th century. But here's the surprising truth. The conical shape of a train wheel isn't about grip or braking. It's about steering. A train has no steering mechanism whatsoever, and the cone is the reason it doesn't need one. Today, we're tracing where the conical wheel profile came from, what problem it solves, and why a shape almost nobody has noticed is the reason trains stay on the tracks at all. The answer is in the shape of every wheel on every train you have ever watched roll in. This is always there, never noticed. To understand the conical wheel, we have to go back to the earliest railways of the 1820s and 30s. A vehicle on a straight track is straightforward. But how does a vehicle with rigid, fixed wheels navigate a curve? A road vehicle steers by turning its front wheels. A train cannot. Flat wheels on a curved track fight the curve, scrubbing sideways and wearing rapidly. Early engineers added flanges, the raised inner lip on the inside edge of every train wheel, to stop the wheel sliding off the rail laterally. But flanges don't explain smooth curve navigation. Flanges are the last resort. The cone is the first. Think of it like rolling two slightly different-sized coins taped to the same axle. On a straight, both coins roll the same distance and everything is stable. On a curve, the axle shifts slightly towards the outside of the bend. The outside wheel now rides on a slightly larger diameter part of its cone. The inside wheel rides on a slightly smaller part. The larger diameter wheel travels further per revolution, exactly as the geometry of the curve requires. The axle self-corrects toward the center of the track without any steering input. This is called natural conicity. The wheel profile turns differential geometry into a passive steering system. No motor, no computer, no driver input. Just a shape doing mathematics at speed. So if the cone is so elegant, why do trains still need flanges? The answer, as is often the case in history, comes down to the limits of any passive system. Conicity works smoothly within a range. On very tight curves, at high speeds, or on worn track, the self-correcting behavior can become unstable. The wheels begin hunting, oscillating from side to side faster than the cone can correct. At that point, only a physical barrier stops the wheel leaving the rail. Flanges are that barrier, the mechanical backstop that catches the wheel when the cone reaches the edge of its ability. The cone steers, the flange catches. Together they have kept trains on rails for nearly 200 years. So, the next time you watch a train round a curve, you'll know there's no one steering it. The geometry of the wheels is doing the work, quietly, at every point on every bend. A cone is a simple shape, but in the right place, it replaces an entire system.